evidence suggests ancient life on the planet Mars. Using Martian sand samples taken by NASA's Curiosity rover, scientists have found chemical clues to the red planet's history. Some of the greatest evidence yet for biological activity on Mars has been published in the Proceedings of the National Academy of Sciences on January 25. However, the fascinating chemistry might be explained by other processes. A river delta and a lake formerly existed in Gale Crater 3 billion years ago, when Mars' temperature was much more pleasant, and Curiosity has been investigating it since 2012. The Curiosity rover has tested ancient layers of watery sediments exposed by millennia of weathering for carbon isotopes as part of its hunt for signs of past life on Mars. Carbon has two stable isotopes, carbon-12 and carbon-13, both of which have 6 protons and 6 neutrons in their nuclei. Carbon-12 makes up 98.9% of Earth's carbon. Nearly majority of the carbon surviving on Earth is carbon-13, which contains 7 neutrons. Carbon-14, an unstable isotope with 8 neutrons, is present in 1 trillion carbon atoms. Its 5,730-year radioactive half-life is used by archeologists to date biological items. 4.6 billion years ago, the original solar nebula, a cloud of gas and dust that eventually condensed into our Sun and its entourage of planets, had the same ratios of carbon-12 and carbon-13 that the rest of our solar system has now. As the lighter carbon-12 isotope forms weaker bonds, it is more likely to be integrated into biological molecules than carbon-13, which undergoes chemical processes at a slower pace. Consequently, compared to atmospheric or geological carbon, biogenic carbon compounds have lower concentrations of carbon-13. Christopher H. House, Penn State, leads the Curiosity team in finding carbon-13 concentrations in Gale Crater sediment samples that are considerably below those reported in Martian atmosphere or Martian meteorites that have reached Earth. It is possible to find stromatolites, layered sedimentary formations, on Earth when carbon-13 depletion is so acute. Microorganisms consuming methane generated petrified mats in these 2.7 billion-year-old relics of some of the oldest living forms, CH4. Currently, the Martian atmosphere contains only minuscule amounts of methane, parts per billion. It's possible that methane is released from underground reservoirs and then dissipates quickly, since Curiosity and the Mars Express spacecraft have observed multiple fast surges in methane concentrations. Martian methane is the subject of much debate. This may be due to chemical interactions between water, CO2, and minerals like olivine. However, the notion of microbial creation remains fascinating. Two chemical processes unrelated to biology and one linked to microorganisms are among the several theories offered by House for the high carbon-13 depletion. All three ideas, however, need further research at this time. Carbon may have been trapped in sediments by methane-eating bacteria on the planet's surface. Methane-eating bacteria may have existed on Mars, although there isn't any hard evidence, such preserved microbial mats, to support this claim, and methane may potentially be bound to Martian surface materials by solar UV radiation and wind-driven erosion. Carbon-13 deficient sediments may be explained in a variety of ways other than by methane. Two possible pathways are cited by the researchers cautiously. The solar system travels through clouds of gas and dust that have different carbon-12 to carbon-13 ratios than the original solar nebula every 230 million years as it circles the center of the Milky Way galaxy. Geochemists have found signs of previous encounters in the microscopic quantities of material that are deposited on Earth during these encounters. The Curiosity team hypothesizes that layers of Martian sand with abnormal carbon isotope ratios formed as a result of cosmic dust gathering on the surface of glaciers and melting. Gale Crater does not contain any evidence of former glaciation, despite this probable hypothesis. The Martian atmosphere's carbon dioxide and water vapor might be converted into formaldehyde and other molecules by UV light from the sun. If this change occurs in the lab, it's not a certainty that it will occur on Mars. Regardless of whether hypothesis is right, all three suggest a carbon cycle on Mars that is unlike anything seen on Earth today. To determine if a future methane plume's carbon isotope ratio suggests a biological origin, researchers plan to utilize Curiosity's mass spectrometer, which the rover will carry with it while it collects and analyzes samples in Gale Crater.